Welcome, everyone. Today we are exploring the Model Context Protocol, commonly known as MCP. If you want Claude to securely interact with your local files, databases, or enterprise APIs, understanding MCP is mandatory. Let's get started. Welcome, team. Today we tackle the Model Context Protocol, universally known as MCP. What exactly is it? MCP is an open, JSON RPC-based standard that allows AI applications to discover tools, resources, and prompts from external servers. In terms of basics, think of MCP as the USB-C for AI. Why was it created? To solve the massive N times M integration problem. Historically, integrating N language models with M different tools meant writing unique, bespoke adapter code for every single combination. It was an unscalable nightmare. How does MCP fix this? It introduces a universal standard. When your AI model supports MCP, it dynamically reads a server's manifest and immediately knows how to interact with it. In our deep dive, it's crucial to note that before MCP, vendor fragmentation led to inconsistent tool invocation. By standardizing the JSON RPC schemas, MCP significantly improves Claude's accuracy and reliability when deciding which tools to call. Take a look at this flowchart contrasting the legacy approach with the MCP standard. On the left, we see the N times M integration problem, where every model requires a hard-coded, direct connection to every tool, creating a tangled web of dependencies. On the right, we see the elegance of the MCP standard. Any model connects to the unified MCP interface, which effortlessly routes requests to tool A or tool B. This single integration point drastically reduces developer overhead and future-proofs your architecture. To build with MCP, you must understand its core architecture. What is it? MCP operates on a robust client-server model designed for secure isolation and persistent context. The basics involve three layers. The host, like Claude Code or Cursor, instantiates an MCP client. This client establishes a dedicated, one-to-one stateful session with an MCP server. Why is this architecture strictly enforced? Because it creates strong security boundaries so that protocols and permissions never bleed across different domains. How do they talk? Entirely through JSON RPC. Every session begins with an initialization handshake where the client and server negotiate their supported versions and capabilities before any work begins. For our deep dive, understand that MCP servers are intentionally lightweight. Each server encapsulates one specific domain responsibility, like querying a database. They can be spun up as local processes using standard input, output, or accessed remotely via HTTP with server-sent events. This architectural diagram illustrates how a single host application manages multiple environments. At the top, the MCP host, such as Claude Code, spins up isolated MCP clients for different tasks. Client 1 maintains a stateful JSON RPC connection strictly with the GitHub MCP server, while Client 2 connects to a local database MCP server. This one-to-one mapping guarantees that the GitHub server cannot accidentally access your local SQL database, enforcing strict, modular security boundaries across your AI workflows. Now let's explore what an MCP server actually offers, starting with Server Primitives Part 1, Resources and Prompts. What are they? These are standardized interaction methods exposed to the AI. The basics: resources serve as read-only context providers, like a log file or a database schema, identified by a URI. Prompts are reusable, predefined instructional templates exposed by the server. Why do we use them? They allow Claude to seamlessly ingest application-specific data without the developer writing custom data loading code. How it works is elegant. Claude can query a resource URI directly to read its contents, or fetch a prompt template and inject specific arguments into it. For our deep dive, the true power of resources lies in dynamic subscriptions. Your client can subscribe to a resource, and the server will automatically notify Claude the moment that resource changes on disk. This guarantees your AI agent always has up-to-the-second context without inefficient manual polling. This sequence diagram maps out a resource subscription lifecycle. First, the MCP client asks the server for a list of resources. The server returns a URI for an application log file. The client then subscribes to that exact URI. Later, when the log file updates on the back end, the server proactively pushes an updated notification to the client. The client can then immediately issue a read request to fetch the fresh data, ensuring Claude's context is never stale. Moving to the most critical primitive, we have tools, also known as AI actions. What are they? Tools are executable functions exposed by the server that allow Claude to actively interact with external systems. The basics involve operations like executing a SQL query, triggering a CI/CD build, or posting a Slack message. Why are tools paramount? Because they transform Claude from a static text generator into an active, autonomous agent capable of manipulating its environment. How do we implement them safely? Every tool is strictly defined using JSON schema. This schema dictates the exact input parameters required. Claude understands this schema natively and guarantees that the parameters it sends perfectly match the server's expectations, minimizing execution errors. Our deep dive reveals that tool outputs are highly versatile. A tool doesn't just return a text string, it can return an embedded resource containing rich metadata or a direct URI linked to an external asset, seamlessly chaining context into the next step of your agentic workflow. Follow the sequence diagram to understand tool invocation. The MCP client initially fetches the tool list and JSON schemas from the server. When the user asks a question, the Claude LLM emits a formal tool use request for QueryDB. The client intercepts this and executes the tools/call over the MCP connection. The server processes the query and returns the data payload, which the client seamlessly injects back into Claude's active context window. MCP isn't a one-way street. Let's look at client primitives, roots, sampling, and elicitation. What are these? These are capabilities the client exposes back to the server. The basics. Roots establish file system boundaries. Sampling allows the server to borrow the user's LLM. Elicitation allows the server to pop up a prompt asking the human for missing data. Why do this? To create secure, adaptive workflows. For example, how do roots work? When you open a project in VS Code, the MCP client sends the current folder as a root. The server now knows it is cryptographically restricted from reading files outside of that specific workspace. The deep dive here is sampling. Sampling is revolutionary. It allows a backend MCP server to request an AI generation task directly from Claude. The enterprise server doesn't need its own Anthropic API key. It piggybacks off the client's secure connection, enabling complex agentic behaviors deep within your backend without exposing raw credentials. This diagram organizes the three powerful client primitives. On the left, roots define the secure file system boundaries. In the middle, elicitation gives the server a pathway to prompt the user directly when it needs human approval or credentials. On the right, highlighted in yellow, is sampling, which securely borrows the host LLM to process microtasks. All three primitives flow into creating a highly interactive, secure execution environment. Let's make this practical and look at implementing MCP in Claude Code. What does this involve? It's configuring your local Claude Code terminal agent to connect with these servers. The basics are extremely developer-friendly. You simply use the Claude MCP add command. Why do we do this? Because it transforms your coding assistant. Suddenly, Claude can query your live PostgreSQL database, manage GitHub pull requests, or fetch live documentation while you code. How do you do it? Look at the sample code. You can run an npx package locally to spawn a server over standard I/O, or use the transport HTTP flag to connect to a remote enterprise server. Our deep dive focuses on scoping. You must be rigorous with your configuration files. Use the project scoped.mcp.json file to store tools that your whole team shares, like a staging database. But for your personal Slack token or private GitHub access, bind that server exclusively to your user scope in your home directory so you don't accidentally commit secrets. This flow visually separates the MCP configuration paths. When a developer runs the Claude MCP add command, a scope decision must be made. If it's a team resource, route it to the project scope, updating the .mcp.json file which gets committed to Git. If it requires personal authentication, route it to the user scope, updating the hidden file in the home directory to protect personal credentials. Let's explore a very powerful real-time use case, building an agentic RAG pipeline using MCP. The scenario: a developer needs help with the absolute latest version of React, and we must avoid model hallucinations from outdated training data. The architecture: we spin up a custom Node.js MCP server exposing two tools, Query React Docs and Search Web. The data source for our docs tool is a quadrant vector database that we've populated with freshly scraped React documentation. Here is the brilliant execution. We write a system prompt dictating that Claude must invoke the Query React Docs tool first. When you ask a question, Claude natively emits the tool call to the MCP server. The server queries the quadrant database, fetches the exact semantic matches, and returns them to Claude. The outcome: Claude synthesizes this fresh data into a flawless answer. We just built a highly sophisticated retrieval augmented generation system where the client just speaks natural language and the MCP server handles all the complex vector database operations. Look at the data flow in this sequence diagram. The user asks the React question. Claude Code automatically executes a call tool request for query React docs to the MCP server. The MCP server translates this into a semantic search against the current vector database. The top document chunks are returned to the server, formatted as a tool result, and passed back to Claude, which finally synthesizes an authoritative, hallucination-free answer for the user. To conclude, let's cover critical best practices and security for MCP ecosystems. First, you must avoid context pollution. Do not load monolithic servers containing hundreds of irrelevant tools into your default.mcp.json. Every tool schema you load consumes tokens in your context window, driving up your latency and your bill. Second, scope tools appropriately. Build targeted, single-purpose servers and use the strict MCP config flag to guarantee Claude only loads the specific tools required for the immediate task. On the security front, always implement a human in the loop for destructive actions. If a tool writes to a database, use the elicitation primitive we discussed earlier to pause execution and force a manual user approval. Finally, defend against injection. Your MCP server must rigorously validate and sanitize all inputs to prevent malicious path traversals. Treat your tools like production APIs. Master MCP, and you'll build autonomous systems that scale beautifully. I invite you to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Thank you for joining me. This final mind map visualizes the 4 pillars of a secure MCP environment. Context hygiene ensures we use targeted servers to avoid prompt bloat. Authentication mandates leveraging OAuth and proper scoping to protect secrets. Validation requires strictly sanitizing inputs to prevent path traversal attacks. And finally, human oversight leverages MCP elicitation to place hard approval gates before any destructive actions are executed.